We're starting a new series of lectures here by Anna on her joint work with these 5 people, and they've solved all kinds of conjectures in a series of papers. And these results have a lot of applications to the study of Catalan combinatorics, dict paths, parking functions, that kind of thing. They also have a lot of new results about LOT polynomials, which we've heard about in connection with the chromatic. So should be of general interest to anyone who's interested in symmetric function theory. Anyway, without further ado, turn it over to Anna.
All right, thank you, Jim. So as I say in the email, today's talk is like giving you kind of like a basic background and the motivation of everything. It is a very tricky talk because we actually talk about lots of the terms in details last year, but not everyone attended last year's lectures. So that's why I decided to just go through things like kind of like in a very vague way, but I'm going to talk about things more in detail in the next 2 lectures. And here, don't worry, I will have examples of almost every term that I have. And if I don't have that, that just means that it's not that important in the lectures. So, and the first kind of like 15 minutes will be quite boring if you're like a lot of your experts. So bear with me, I'm going to, but this is suitable for whoever just learn about like symmetric functions. All right, so let's get started. So this is a joint work with Jonah, Mark, Jennifer, and George, and we have been working on something called cat and animal, and I'm going to talk about what they are. So let's start. So like in John's lecture, he used the algebraic approach to define the Schur functions as characters. Here, I'm going to give you an other like definition of the Schur functions, which will give you exactly the same polynomial. So a Schur function as mu is defined like this. So what are these? So we use S just because it's the Schur function. SSYT stands for semi-standard Young tableau of shape mu. And what it is just fillings of positive integers. You can think about it as like Sudoku with some like rules there. So you fill in the boxes in the Young tableau, like a diagram, so that the rows are weakly increasing and then the columns are strictly increasing. And here I'm going to use the English notation. So this is an example of a semi-standard Young tableau of shape 4331 because 4 boxes in the first row and then 3 boxes in the second row and so on. And you can see that rows are weakly increasing and columns are strictly increasing. So that's the SSYT. Now with XT, well, XT is just saying that XI to the power of the number of i's in T and multiply them together. So let's say if we have this tableau and then we want to calculate xt, then what it means is like I have x1 squared because I have 2 1s, x2 squared because I have 2 2s, x3 to the power of 1 because I have only one of them, and x4, x5 cubed, no x6, and then x7 squared. So that's x to the power t. So as mu is just you fix a shape, fill in the integers, satisfying weakly increasing row and strictly increasing columns, calculate their corresponding monomial like this and add them up. So that would be symmetric actually. Okay, so give you a full example. Say I want to just look at x1, x2, x3, and then I want x21 in these 3 variables. What it means is that I have the shape 2, 1, and then I just fill in 1, 2, and 3, satisfying the weakly increasing row and strictly increasing columns. And these are all the possible things. Each of them gives you a monomial. And then you just add them up. And then you get the Schur functions 2, 1. So that's that would actually be the same as the irreducible character definition that John talked about in lecture 2. And some interesting that there are lots of interesting things. One of them is the Peary rule. What it is that, okay, well, I have these Schur functions and then S21. So this is the S21 in infinitely many variables. And then if you multiply with the Schur functions of the shape with 1 row shape, then of course I can just multiply them together, but it looks very hard. And then we know that the Schur functions give you a basis. So after you multiply them together, you want to break it down into like write in terms of Schur basis. Then how do you do that? So that would be extremely hard. But the period rule gives you a very clean way to do that. So you have this shape 2, 1, and then you have like a row shape 2. Our goal is to just use these 2 yellow boxes and then stick at the boundary so that I can still get a partition here such that no 2 yellow boxes in the same column. So how can we do that? Well, we can just do it like this, or like that, or like that, or like that. And these are the only possible ways that we can do. And so we record all the shapes, and that gives you the Schur expansion of the product. So the period rule gives you kind of like a very powerful way and simple and clean way to write the product of 2 Schur functions into Schur functions. So Schur functions is a very important symmetric functions in the ring of symmetric function over Q. So if you upgrade it, kind of like have a newer version, if I change the base field as the rational polynomials in T over Q, then the Schur function will upgrade to Hollywood polynomial. And then if you upgrade it more, if your base field is QQT, then the Hollywood would upgrade to Madonna polynomial. Just to give you some like example. So we already know what's S21. And then if we upgrade it to the Hollywood polynomial in T, then it is like I use Sage to compute this for me. So this is actually S21 minus this. So you can expand it and you get another symmetric functions, but the coefficients are now with some T's. So if you want to get back to the Schur functions, you can simply put T equals to 0. And then the Madonna polynomial, now you have 2 parameters Q and T. And then you can see that it's not that nice looking, but the coefficients here are in Q and T, but rational functions, right? So you have some kind of rational functions in Q and T, and then you can still write it in the Schur basis. If you want to get back to the Hollywood, you just put Q equals to 0. If you want to skip the step and just jump from the Madonna to the Schur functions, you can just put Q equals to T, as long as Q is not 1. So that's like, you can see that that's kind of like a relation. You can think about the Madonna polynomial as a generalization of the Schur functions in the ring of symmetric functions over QQT. Now, so this is the Madonna polynomial that I give you. So that's the original definition. If you do some kind of change of variables, we call it parallelism, and you will get something called a modified Madonna polynomial. And why do we care about this? It's because, first of all, it has a very nice combinatorial interpretations of like the modified version. Secondly, is that later on, I'm going to show you that, remember in the P version, you have this ugly coefficient in a rational function, where you write in terms of Schur functions, but actually in the modified version, when you write it in terms of Schur functions, the coefficients are actually very nice. So that's why we usually look at the modified Madonna polynomial. And
Anna,
yeah.
I know you have mentioned specializations Q0, T0, Q equal to T, but what if you try to do like a Laurent Q and Q minus 1?
And oh, you mean like
instead of T, you write Q 1 over Q.
1 over Q. So you were saying if I just put in Q as 1 over Q? Is it what you said? Or the T as
is 1 over
Q inverse? I don't remember on top of my head, but I think that is something. So Jim may know even more.
Yeah, it doesn't reduce anything really simple.
Right.
It's a little simpler than the general, but it's not like the QT Catalan that just collapses to a binomial coefficient.
Right. So, but I think some people look at that before because I vaguely remember that there's like a specialization when people put T equals Q inverse, but I don't remember the results that I saw. But that's an interesting question. All right, so like one other interesting thing that I can talk, well, several interesting things I can talk about in Madonna polynomial is that like you have this Q and T, right? If you switch the Q and T, so now you have T and Q. This actually is the same as the QT version, but now you conjugate your partition. So conjugate means that row becomes column. So this actually, we still don't know the combinatorial proof. So if you're interested, you can work on this. Another interesting thing is called a Nabla operator, which is the very essential element in talking about the Loehr-Warrington conjecture. So where's a Nabla operator? So a Nabla operator is just an eigenfunction that you add on the modified Madonna. Then you get back a modified Madonna with some QT here, okay? So it is just like the Madonna polynomial, the modified Madonna polynomial is like an eigenfunction, and these Q and T are eigenvalues because they are constant in our ground field, right? So these N are just some statistics. To calculate it is actually very easy. You can just draw your shape and then fill in zeros on the first row, ones on the second row, 2 on the third row, and so on and so forth, and then add all the numbers that you fill in, then that is what it is. So these are the ends. So like, give you an example, when mu is 2, 1, then even if you don't know what the QT power is, you know that it must give you back the H2, 1 because it's like the eigenfunctions, the eigenvector. And then now the eigenvalues are QT. It's just because when you draw the shape 2, 1, then the only thing that you can put in is 1 and 2 zeros. So you add up to be 1, even if you conjugate it. So that's that. So Nabla operator, you can think about is just an eigenfunction with like the Madonna polynomial as the eigenvector, and then with some QT as the eigenvalues. If you want to know more, this is actually this is first defined by Francois Bergeron. So this is from his website. He wrote this letter to Adriano Garcia, and because I don't know any French, so if you know French, then you would know the history of like what he was looking about. But this is just like a letter that you can actually find on Francois website if you want to know more. All right, so in algebraic combinatorics, what we actually always look at is to link our combinatorics and also algebra and geometries together, right? So we want to like borrow things from the algebra and geometry to prove things in combinatorics, or in the other way around. We may want to prove things in the other side by using combinatorics. So I'm going to like talk about like, okay, what are the things that people in algebra sometimes would look at? So one of the things that people usually look at is like, okay, I have a module and I want to break it down into like smaller pieces until I cannot. So these are like the blocks that you cannot, it's just like atoms, right? So you want to break it down into like this. So these are like the irreducible blocks. So in symmetric functions, okay, just give you an example. Our sure functions are these blocks. They are the irreducible GLN characters. So you cannot further decompose them. And then the Peary rule that we talk about, basically is just telling you how to decompose, right? You have two sure functions multiplying together, and then you break it down into sure functions. So what it means is that you just like, you multiply them together, get something bigger, and then you decompose them. So the Peary rule gives us a combinatorial way to decompose the product into the irreducible blocks again. So that's basically what Peary rule is. And now, of course, by the same kind of like idea, I have this modified Mathernal polynomial. Can I break it down into the shear function? So can I break it down into like smaller pieces, right? So, well, we can always do that because shear functions is a basis, right, in the ring over Q. So you can always like just break things down, writing in terms of the shear functions. But now your coefficients is something in Q and T, but rational functions, right? So maybe ugly things with refractions. I don't know, right? But then when you try to compute them, which is actually very hard to compute, and when you compute them using your computer, you realize that all these coefficients are actually not that ugly. They are not fractions. They are just polynomials. And furthermore, the polynomials has no negative terms in the coefficients. All the QT things, if you look at the coefficients, is a polynomial in Q and T, and then all the coefficients are actually just non-negative integers. So that's really cool. So now, how do you prove something like that? Well, when you see the non-negative integers, of course, we want to find a combinatorial way to prove it, but unfortunately, we still don't know how to do that. But Mark Kamen proved this using geometry. So to give you just a very vague idea, what happened is that Garcia and Heyman study a module called a Garcia-Heyman module, of course. And so this module lives in the ring, like the polynomial ring with two sets of variables over C. And then that's kind of like the famous n factorial conjecture. So they computed that the dimension of this module is n factorial. So this guy is isomorphic to an Sn representation. Okay, so now this is a module, right? As I said, if you have a module, you want to break it down into smaller blocks. So to break it down into smaller blocks is something called a Frobenius map. So you break it down into smaller blocks and look at the coefficients here. So these give you the Hilbert polynomial. And these guys are in NQT. So now you have this problem in hand. You're studying this thing. And then these guys are NQT. So if we can somehow relate these two things together, then we prove the theory, like this conjecture, right? So Mark Kamen realized that, oh, I can use geometry to talk about this. So he used the Hilbert scheme Xn on endpoints in a plane, and then link these two guys together. Okay, so then because we already knew that these guys are polynomials with non-negative coefficients, then of course this guy is also right. And now then that's great because these two guys are equal. I sum all these things times S lambda. What it means is that the Frobenius map of this module in Q and T are basically just the modified Mathernal polynomial. So you can actually view modified Mathernal polynomial as the Frobenius image of this module. All right, so now that just means that I start with a symmetric function in Q and T. I have the Hilbert scheme. I have the Garcia-Heyman module. So that just means that I am linking algebra, geometry, and symmetric functions together. So this is kind of our goal, right? We want to link algebra, geometry, combinatorics, and symmetric functions together. So now the question is, can I add the combinatorics there? Well, there are some combinatorics already because like to define the modified Mathernal polynomial, Heyman Loehr actually has a very good paper on how you do that using tableaus. So, but unfortunately, we still don't know how to prove that these guys are in NQT combinatorially. So this is still open. All right, so by thinking about the same thing, and I'm going to talk about another version of something similar. So it's called diagonal harmonics. So what is this? It is just like you mod the ring of the polynomial ring of two sets of variables over C by some ideal. These ideals are just generated by all the Sn invariants. So you can think about it, symmetric functions in the x1 and y, like the xi and yi without constant term. Okay, so the constant term is 0. So you mod that, and that gives you the diagonal harmonics. So that gives us a module. And this module, if you calculate the dimension, just like last time we calculate dimension, we realize it's n factorial. This time, if you calculate the dimension, you get the n plus 1 to the n minus 1. So if you're in graph theory, you already knew that this is the rooted tree, number of rooted trees on n plus 1 labeled vertices, which actually is also the same as the number of parking functions, right? So, and if you look at the multiplicity of the sign character, is actually the Catalan number. So you can now think about, okay, well, it relates to trees, parking functions, and dig paths, right? And so if we do the same game, we have a module, we want to break it down into smaller blocks, right? And we have something like this, okay? And then again, these polynomials are in NQT. So now Mark Hillman said, okay, well, maybe the Hilbert scheme can come in and help you with something. So he looked at this, and then this Hilbert scheme gives a geometric meaning of this module that we look at. So that just some like geometric meaning. For example, the DHN is actually the coordinate ring of the scheme theoretic fiber over the origin, global sections of the structure sheaf on a fiber in XN. So basically what it is that I have this module, and then now if I use the Hilbert scheme, what can I say geometrically on this module that I'm looking at? So there are some geometric meaning there. So now the missing part is the symmetric function and the combinatorics, right? We have the algebra, we have the geometry. Where is the combinatorics or the symmetric function? So actually, this guy that we are looking at is Nabla of S1n. Isn't that cool? Because like now suddenly the symmetric function size suddenly appear with the Nabla operator. So that gives us the symmetric function, right? So this is actually the shuffle theorem. So the shuffle theorem is saying that, okay, well, I have this DHN module, I have like a Frobenius image, right? And then I can link them to the Nabla. So I have symmetric function, algebra, and geometry. Where is the combinatorics? So the shuffle theorem is going to give you the combinatorics. And the combinatorics is using the dig paths, which we saw like a hint when we already see that like the dimension is related to the rooted trees and parking functions and the dig paths, etc. So this is the shuffle conjecture.
Anna, Anna, before you go,
yeah.
on the previous page, you have the symmetric functions coming into the picture.
Right.
And I'm just asking a curious question. In this program, general program that you has been done, you're doing, is there a quasi-symmetric function version that's to relate to the papers that we learned last month? Oh,
you mean the chromatic quasi-symmetric functions that's related? It's actually will come into, there will be some relation here. So it's actually the next slide here. So these guys, G here, are the LLT polynomials. So when you have the unicellular LLT polynomials is defined by kind of, you can think about, it's a generalization of the shear functions. So you have different blocks. So if all the blocks have like one cell, then that is actually related back to our chromatic symmetric functions. So there is some connection between that. And also Carlson and Millett, when they are proving this, they also have something related to the chromatic symmetric functions or quasi-symmetric functions. So there is like actually closely related.
Thank you.
Sure. All right, so this is the shuffle theorem. What it is just, okay, well, we know this guy using the Frobenius map. Like you can just think about, okay, well, to calculate this, I can first of all calculate what is the DHN, and then I can just use the Frobenius map, and then I can just calculate the Nabla of S1n, right? So then why do I need this? Well, because there's no combinatorics. And here, this theorem gives you the combinatorics. And there are two types of combinatorics here. The LKK are the paths. And this G here is just LT polynomials. Like Teddy was just asking, what is the relationship between this and also the chromatic thing that we learned for the last month, right? So the LT polynomials has connection to the chromatic symmetric functions or chromatic quasi-symmetric functions. And so that's like a connection here. So let's give you an example of what this is, okay? So Nabla of S1K, so now my K is 3. So what it is that lambda in LKK, this lambda are just the paths. So so I have this path, the yellow is the path. So I want to draw paths which are under this red line, and this red line is from 0, 3 to 3, 0. So you draw all of them. Area is just the number of complete boxes between the yellow line and the red line. So that's why area 3, 2, 1, 1, and that's no complete squares here. So area 0. Themes is some statistics. And then I computed the LT polynomial for you and write it in terms of the shear functions. So there you go. And then now you add them up together. So you can see that, okay, well, there are some negative here, right? So that doesn't seem like our QT thing. But if you multiply them, if you expand all these parentheses, you will see that like the Q inverse, when you multiply with each of them, would disappear. Like you don't have a negative power. The Q cube would take care of all these like negative powers. So that actually will give you something positive in QT, like when you write in terms of the shear functions. So that's very interesting here, right? So now let's look at our like Nabla S1n. So what happened? Okay, well, as I said, it described the DHN as a doubly graded SN module. So you can just think about this Nabla of SN is the image of the Frobenius map of this DHN module. And then it gives a QT analog of the associated combinatorial objects. It also connects specializations of some previously known Q analogs. So you can specify your T, and then you can like have more connections to that. So that's great, because by looking at the diagonal harmonics, we actually link, again, linking algebra, symmetric functions, combinatorics, and geometries together. Right, so that's kind of like our goal in the algebraic combinatorics. So that gives you like a background of this Nabla operator and what people are looking at. And the next thing that I want to talk about is the main, like a major thing that we discussed last year in IPAC. Is something called Catananimal. Is the project that my group is working on, which help us to prove a lot of stuff. So what are these like? We usually just call it cats. Okay. All right. So briefly giving you an idea what they are. So first of all, you pick your L. Okay. So look at your GLL, look at all the positive roots. All these alpha ij is simply just like epsilon I minus epsilon j, meaning that you have 1 in the I position, minus 1 in the j position, and 0 otherwise, with a length of L. So you have, for example, alpha 1, 2, it's just 1 minus 1 and a bunch of zeros, right? So you have a set of all these positive roots. Now you just choose any root set here, any root, like usually we would take root ideals, but you can actually take any root set. And then you take your favorite integer sequence with length L. Now I'm going to define this guy. So that's our cat. We have the free root set that you choose. You have the sequence that you choose, and this is what it is. So it looks very complicated with the examples. You can look at a lot of examples in my website, but for now, most important thing that you look at here is that like this W in SL. What is this going to do is that, okay, you give me one term here, right? And then you just symmetrize. So then summing up all the possible way that you permute them, that guarantees that that's a symmetric function. And all these, like you say like, hey, that's like rational, that's not like a polynomial, right? It is not polynomial, it is a series. So you can actually, after you compute these guys, you know, like 1 minus something is like the geometric series that you become 1 plus, like for example, the first one here, 1 plus qx alpha plus q square x2 alpha plus q cubed x3 alpha and so on. So you use that, multiply them together, have a big chunk of things. And then afterwards, you can actually decompose them into reducible characters. But for now, just think about this is a way to create a symmetric function in a very complicated way by choosing.
Just to make sure, in the RT product, that's a minus alpha as opposed to a plus alpha in all the other products. Okay, just making sure.
Okay, and also Anna, just to try to get intuition, this is the first time I'm seeing this in this way. Are there some conditions that you're usually going to put on these sets, RQ, RT, RQT? Like, will one be contained in another, or?
So like usually when we do like our normal thing, like for example, Macdonald polynomials, we have a generalized version of this cat and animal, and then we would like require Q reset is bigger than, like RQT is the smallest, and then RT is bigger and so on. But in general, this thing can work with things with holes. You can actually pick things out. You don't even need to have a root ideal.
And we're always going to get a symmetric polynomial no matter what sets we pick. And okay, cool.
Yeah, it's because of the W here, because it like guarantees that everything is symmetric.
And it will be a polynomial because there's cancellation that happens.
That is not a polynomial. It's
it's not
series.
Okay, thank you.
It's a series. Yes. So it's a series. So and then later on, like we will see that we truncate it so that we only look at the polynomial part. But the polynomial part means that, like, first of all, you have this series with things which are negative, right? And then you write them into the chi lambda, where the lambda can be negative. But if you truncate it so that I don't care about the virtual GRL characters, I only look at the S lambda, then that guarantees you to have the Schur functions, right? Like a sum of the Schur functions. So that is the idea. But this guy, you're right. It is not a polynomial. It is a series.
All right. Thank you very much.
Sure. Yeah. So this thing is very interesting, like, because you can actually have the same thing on the right hand side, even like there are more than one way to create the same cat and animal. So maybe I choose some Q reset here and you choose some Q reset your way, and you may create the same thing. Okay, so it is not like a unique way, like a one-to-one thing. It's not. So you can put holes inside there. You can just pick some random subset here and then create your own cat and animal. It's really your DIY. And there are lots of things that we don't know about this thing. So that's a very interesting thing that we are looking at. So that's our cat. Yeah, so we actually have like lots of like, so that's why you can create your own cat. And you will see that we create our own cat to prove the Loehr-Warrington conjecture. All right, so give you some special thing. Why do we care about this, right? So this is actually like if you pick, say, you pick the full reset for the Q, and then I just don't pick anything for the RT and RQT, this gives you the dual Hollow-Wood polynomial, okay? And then if you want to look at the irreducible GRL characters, what it is just you pick empty set for everything, okay? You don't pick any positive root for any of these, you will get back your chi lambda. And if you choose your lambda to be partitions, then you will guarantee that you get the Schur functions, okay? So this is just like a big package, and then it includes a lot of things that we know by choosing the right reset. So you can also choose your root set carefully, and then you can get your K-share functions. You can talk about the NABRA on LT polynomials. And we also have a modified version on the Madonna polynomial. So we call it mechanisms. Okay, so there are like a lot of versions that you can play with it, and it actually include a lot of things that we know. So that is purely algebra, right? Algebra and symmetric function here. So now the next thing, of course, is like, okay, well, is there any geometry? And that's why Mark Kamen is in our project group, because he knows a lot of things about the geometry here. So he taught us the elliptical algebra. In our paper, we also call it the Schiffman algebra. So these are just like the definition of what they are. So the elliptical algebra, or the AKA Schiffman algebra, is just the Hall algebra of the category of the coherent sheaf of an elliptic curve. And so for me, I am not very good at the geometry. What I know is that this guy is isomorphic to the limit of double affine Hecker algebra for GLK as k tends to infinity. And the only important thing here for this talk is that this guy has two parameters, m and n. That's the only thing that I want you to know. The second thing is that it actually would give you a geometric construction of the Madonna polynomials. And the third thing is the one that I care most. It is like, it looks very complicated to someone who does not know geometry that well, but it actually is just copies of the symmetric functions. So when I look at this, for me, I'm just looking at it as like many copies of the symmetric functions, and that's it. So if I give you a symmetric functions, because it's a bunch of copies, right? So you choose your mn. So what it is like the two parameters, you choose your mn. Each of the mn gives you a line. Each line is like the multiverse, you know, like, I don't know if you're into MCU, but like the superhero thing, but there are lots of like timelines and multiverse. So each of the mn that you choose is like your timeline or your multiverse, and you just go into your universe. So choose your universe. And then each universe is a copy of your symmetric function ring. And then now,
do you have finite or infinite universe?
Is
Lines.
infinite.
Lines.
Yeah, lines. So it's like any slope that you can think of, any rational slope that you can think of. So it's countable, but it's not like it is infinite. So there are infinitely many universes, but there are countably many. Yeah. So that's like depending on your mn. So m and n are integers. So pick your relatively prime pairs, and then like you just, each of them gives you like one universe. So each of them is a copy of the symmetric function. So this is what the elliptical algebra is in my point of view.
This is in view of Dick passes or something.
So so now if I give you a symmetric function, you choose your universe. So that's the mn. The corresponding image in your copy, like in that copy, in that universe that you choose, is actually just this guy. Okay, so you can ignore all these technical details. Important thing is that give me a symmetric function, I can find your image in that universe, and that image looks like this with the mn. So the mn is kind of like a label of which universe that you chose, and that's it. Okay, if you fix n equals 1, and this universe can add on the symmetric function, the NABRA to the power m, so you can apply the NABRA m times on a symmetric function, is basically just your image adding on the symmetric function 1. So that's very interesting, right? Like these are purely symmetric function thing, and this is like the coherence sheaf and like elliptical algebra, like geometry thing, and they have an action on the symmetric function. You just simply add this guy on 1, and then you choose your universe such that this n is 1. Then yeah, then you get the NABRA m of f.
So Anna, I remember from last year, so the xmn, this whole thing on the right is an operator, right?
Right.
xmn.
Right. So like for this xmn, so xmn are just variables. Like in our symmetric world, we only have x, right? x1, x2, x3. And so our alphabet is x. And then because in the elliptical algebra, each line gives you an alphabet. So the xmn is just a set of alphabet. So for example, in sure functions, we write s lambda, x1, x2, x3, right? And then say, for example, I choose the universe 1, 1, okay? Then in that universe, all the variables, instead of you write x1, x2, x3, you write it as x1 and then 1, 1 on the top, x2, 1, 1 on the top, x3, 1, 1 to the top. So it's just a label. So
Okay.
they are alphabets. And each of them here is just like an element in the elliptical algebra. So it's just something. They have some relation between them. You can act like you can multiply two things together. There are some rules that we talked about last year. But if you look at it as an algebra that you can add on another ring of symmetric functions, so that's the action here. So that's an action. So you can think about it as an operator in that way when you add it on the ring of symmetric functions.
Right. Okay, thanks.
Sure. So give you an idea, like we have been talking about the shuffle theorem, which is Nabra adding on S1, right? So that just means that my M is 1, and then my F is this sure functions. So I just put this F as a sure functions, my M becomes 1. And then, so now I have another version, right? Like I can describe this thing, which I know how to explain it as an image of the Frobenius map of the diagonal harmonics. I know how to talk about it in dict path. Now I can talk about it as an action of the elliptical algebra elements adding on the symmetric function 1. So I have another explanation of this thing. So that connects the whole shuffle theorem with the elliptical algebra, which is very cool. But now, where's our cat? Right? I talk about the cat and suddenly I change gear to this elliptical algebra. Is there anything related to these two guys? And the answer, of course, is yes. So how do we connect these two together? Well, not all the cats can relate to them, but there's something called the tame cat, okay? So if we can find some tame cat, meaning that you choose your RQ, RT, and RQT reset in such a way that satisfy a bunch of like conditions, then you're a tame cat. If you give me a tame cat, I can associate another like object in this elliptical algebra. So choose your universe again. Each universe gives you something. So you have your cat, choose your universe. I can find someone in that universe to relate to you, okay? And because as I said, this universe is governed by the symmetric functions, right? Because it's isomorphic to symmetric function ring. So they are governed by these F. So this F that we chose, we call it a cup of H, okay? So we have a big cat and a small cat. So that's how they related.
Is it a unique association?
Yeah, so this has a unique F that associates to it. So give you an example, I can choose the whole root set here, like a whole positive root for the T, and then just out plus here is the QT reset, which you ignore the alpha ij where I and j differ by 1. So basically it's just off one diagonal, and then you choose all ones here. This is a tame cat. This tame cats associate to our S1111 when you choose your M and N at 1. So that's cool. Why? Because remember this guy, if you add on 1, it's just the Nabra of S all ones, right? And we know that, oh, this guy, if we use the elliptical algebra interpretation, it's just this guy adding on 1. Now I can just tell you the relation between this guy and also a tame cat. So basically, I can find a cat that associate to the Nabra of S1111. So now you can see that I linked the cat with the elliptical algebra, and then link the whole thing to the shuffle theorem. Okay, so that's how the CAT comes in. So the CAT has a lot of interesting thing. It links to the elliptical algebra. Elliptical algebra also links to this like Nabra or delta operator. And then the CAT and animal actually, there are some of like, they are related to something called LT series. And these LT series also link to something called non-symmetric correlative polynomials. You don't need to know what they are. For now, I just give you a kind of really broad picture. And then if you truncate these LT series, you get the LT polynomials. And also this series relates to some paths, okay? So some lattice path thing. So now you can see that I link with this CAT and animal. It's kind of like become the media to link your algebra and geometry to the combinatorics. So it's basically going back to what I said, like in algebraic combinatorics, we always want to link these two worlds together. And CAT and animal actually serve that purpose. So,
Yeah.
Yeah.
When you truncate to get polynomial from the LLT series, where do you truncate? How do you decide where to truncate?
Yeah, so you get this series and then you use the irreducible characters to, so you have a series right in terms of the irreducible characters, so it's like having blocks, right? But because they are series, so you have negative powers, meaning that your chi lambda, some of the lambdas have negatives, okay? So to truncate, we just ignore all the chi lambda where the lambda has some negative. So you truncate all of them, then you would remain as writing in terms of the S lambda, because you have no negative, you can just write it as like any lambda with positive entries, right?
It's like taking the analytical part or something.
Exactly, yeah. So, so you can see that with the big CAT and this cup, it links to so many different things. You have like LT series, elliptical algebra, half algebra, non-symmetrical little polynomial, many things. When you combine them, it just gives you like a very big tool. And this powerful tool actually helps us to generalize the shuffle theorem under any line instead of just the fixed line from 0k to k0. It helps us to prove the extended delta conjecture, which also in turn to prove the delta conjecture. It gives you an explicit raising operator formula for the Nabra of LT polynomial, because our way to define the big CAT, the CAT and animal, is basically like a raising operator. And then we prove the Warrington conjecture by looking at a special CAT. And also we modified it to prove like the McDonald polynomial raising operator formula. Anyway, so that's our CAT. And then, so give you an idea of what the CAT can do is that, remember this slide with the shuffle theorem and then all these things, right? So we generalize, and then we have some elliptical algebra thing adding on a 1. So instead of adding on any line like this, you can do it like shift it to any slope that you like, any negative slope that you like. And then, so we just simply change the combinatorial side by a little bit, and then we get a formula. And so that's linking our elliptical algebra and then get this, okay? So if you put, so this guy, again, because it's elliptical algebra, and then we have a way to link it to the tame cats, right? So all these tame cats are of this form. If you put all these b's as all the ones, sorry, if you put all these b's as ones, okay, whoa, then that gives you back the original, like the shuffle theorem. So that's what I want to say. All right. So of course, the next thing, of course, is like, okay, well, we always look at the S lambda with lambda all ones, right? So what about S lambda for any lambda? So that is what the Warrington conjecture comes in. So it is a conjecture in 2008. And it says that, okay, well, Nabra of S lambda, they give a combinatorial interpretation of here. So you have some paths, some statistics, writing it in terms of LT polynomials. So again, LT polynomials can be defined using tableaus. And so that's combinatorics. And they also have like a version that can do nabla to the power m. Now the path, you have many paths, and they call it the labeled nested path. So what is LNDP just stands for that. Okay. So give you an example. This is the original conjecture, the Warrington conjecture. You choose your lambda and then calculate all these statistics. The only thing that I want you to look at is that we have all these paths, right? And then they are nested. So they have different ways, like you cannot have like a share. I think in this case, you don't have a share E step. And so you have some nested paths. And then each of them will give you some tableau boxes. So from the path, you get tableau. When you write tableau like this, you define the LT polynomial. Okay, so that's how you link the nabla as 322, and then you have calculate all these like statistics, and then you add them up, and then you get what you want. So it basically gives you a way combinatorially to decompose your nabla of S lambda into LT polynomials. So our TeamCAT comes in again, because remember, like if I have like the elliptical algebra, if I choose my F, instead of S all ones, I choose S lambda, right? I can find my TeamCAT, right? And then if I have the elliptical algebra to add on 1, then it gives me back the nabla to the power m S lambda. So that links everything. So the TeamCAT here actually gives us a media to talk about this guy, right? Using the cat, and because the cat is related to LT polynomials, that gives us like a clue to how to prove the Warrington conjecture. So by choosing the right cat, we actually prove the Warrington conjecture this way, and we also can generalize it to an MM version using the elliptical algebra. So what it means is that we choose Mn instead of M1. So we have an MM version of the Warrington conjecture. So that's like a very powerful tool here. And so give you like a history of what's going on. As we said in Francois French like document, the nabla operator is defined in 1994. And then we have the shuffle conjecture in 2005. And a lot of people try to prove it by generalizing into different versions, so that if one of them is like proof, then they can specialize to get back the original one. And Warrington used another way to generalize it in 2008. So for all these things, we like by 2008 is still open. And for the nabla operator, you also have another version called the delta operator, which was specialized to the nabla operator as well. It's defined by, I think is Jim Hagland, Jeff Brimall, and Andy Wilson, I think, right, in 2018. And that also gives you something like another conjecture called delta conjecture. And again, to prove it, there are different kind of like extension of it. And then if each of them, if any one of them is proved, then you can prove the delta conjecture. During the same year, Carlson and Miller proved that the shuffle conjecture becomes a theorem. And then they prove it by first proving the compositional shuffle, and then they prove the shuffle theorem. Okay, so these two are proved. And then our group using the cat generalized the shuffle theorem in 2020. And then in the same year, the compositional delta was proved, and then therefore proved the delta conjecture. And our group in the same year also proved the extended delta conjecture of the Rice version and proved the delta conjecture. And then our group used this kind of like a similar method and then proved the Warrington using the CAD in 2021. So this kind of gives you a picture of what's going on during these years. And I don't think anyone actually know how to prove the extended delta conjecture in the value version. Yeah, so there's a lot of things that we don't know. We still don't know. All right, so yeah, so like I have 5 minutes. So like just give you like an idea of how you link the shuffle theorem to the Warrington conjecture. I have been using S1 to the power k, but it's just EK. So now I'm going to use EK here. So we know nabla of EK is just this, right? Using the LT polynomial. And then you can actually extend it to something called KMKN shuffle theorem, which basically is just using this operator, or you can think about it as the like the Schiffman algebra that we have, adding on a 1, then you have this, right? So when n equals 1, it gives us back the nabla M EK, okay? So you have this KMKN shuffle theorem. When n equals 1, you get the nabla of M. When m equals 1, you get the original classic shuffle theorem. So now, if we change everything to sure, then it actually gives us the same thing. So that is what we call the Warrington theorem. Instead of EK, I just write it as S lambda. And when n equals 1, I get nabla M. When m equals 1, I get the nabla. So these are the classic Warrington theorem or conjecture. And then this is our version of the MN Warrington. Now, what is missing is that I'm just giving you the left-hand side. All these theorems are like interesting because we are talking about the right-hand side, like the combinatorics linking to nabla of the symmetric functions. So how can we describe these guys using some combinatorics, right? So our major theorem that I'm going to talk about in the next lecture is this. So this is our version, right? Instead of E, I put the S lambda, NE S lambda. And then we have a bunch of like very complicated things on the right-hand side, okay? And, but it's just basically some LT polynomials, some PAPs, something called nest, and then they're just combinatorial objects, all right? And, okay, so we come up with this. The very first question that you may have would be like, how do you prove something like that, right? So I'll give you a very simple proof using the cat, okay? So what do we know? Well, as I said, like if you give me any symmetric function, choose your favorite universe, you have your elliptical algebra element here, you can find a cat, right? You can find a tame cat. And then if I choose my F as the S lambda, then of course I just change my F to S lambda. So I have our sure cat. And then the whole paper, which is 60 pages long, is actually telling you how to relate this cat to something called a den and nest, okay? So we found a way to link the cat to some combinatorial object. Next thing that we know is that if you add this on 1, it's the nabla stuff, right? The left-hand side is the nabla stuff. And then we realize that you can actually write it in terms of, you do the truncation that Teddy asked it. It's just like you truncate your cat and then do the omega, the symmetric omega, and then have some QT polynomial in front. So that's basically it. So we proved that this in like one of our paper. So now what it means is that if I choose my F as S lambda, I can just change all these guys as S lambda. So I have a S lambda on the left-hand side, and then we have some mysterious CQT and some truncation of our sure cat, right? So the main theorem in our paper is saying that if you truncate your sure cat, it is actually a sum of LT polynomials. So that's that. If I know this, I can just replace this omega polynomial truncate cat. It's just our CQT summing up all these LT polynomials, right? So that's great because now that's how we get our theorem there. So the whole thing is that we have to understand this cat and how it relates to our theorem. So next time I'm going to talk about all these notations in more details and then tell you how you can use all these, like if you give me a lambda, how do you do that on the right hand side? All right. So I will stop here for today.
Okay, let's thank our speaker for all the wonderful animations and results. So, any questions for Anna?
I had one more question.
Mm-hmm.
So the CQT
Mm-hmm.
that you get, that constant outside, that depends upon F, right?
Right.
Okay, good.
Yeah.
It didn't have any F's in it, so I
Yeah,
just
yeah, sorry. Yeah, it's just some constant, like it changes based on your F.
with
Yeah.
F, it
Yep.
it's upon depends.
Yep.
Is that a rational function or a polynomial?
It is a polynomial.
So great talk. So so your cats and tame cats.
Mm-hmm.
Do you have any idea when they're sure positive or sure negative, kind of like in the Loehr Warrington conjecture?
So we know that some cats are not sure positive. That's unfortunate.
Or mixed signs even, yeah, so.
Yeah, but there are some of them, like it really depends on the conditions that you choose. There are some conditions that you impose on the way that you choose your RQ, RT, and RQT that will force it to be positive. Yeah.
Okay.
But in general, cat and animal is not sure positive.
And the condition of being tame, is that a condition that you can state in terms of RQ, RT, RQT, lambda, or?
Yeah, it is a very complicated like condition. Like even when we are trying to calculate it, it's just like you have to use a computer. It's just impossible. Yeah, the conditions is very hard to track, but like once you satisfy those conditions, then yeah, you can get the tame cat, and then like those are like sure positive.
Okay.
Yeah.
Anna, I have a question. This is probably a little bit unorthodox. This is for you or people working in this area. In your calculation, in your discussion, you had M and N, which are related to slopes of lines.
Right.
And so, but that reflects that the slopes are rational. And now, is there any consideration? I don't know if it is combinatorially meaningful, but what if the slopes are irrational, and like you can take the limit of rationals?
Oh, that's interesting. I'm not sure, because like everything I know comes from Mark. So like I can ask Mark. But something interesting that we use actually a lot is that like you see our line, right? Like the M over N. When we do the combinatorics, we actually shift it a bit so that it is irrational, to make sure that our combinatorics do not have ambiguity. But I'm not sure that is anything related to your question, but that's a very good question. I should ask Mark actually tomorrow when I see him.
Okay, thank you.
Sure. Oh, okay. So Ji-sun has a question, right? Are there any interesting of the dimension of the, so in the track I saw that like there's like an n factorial or like the n plus 1 to the power n minus 1 conjecture. Are there any interesting dimension of the Loehr Warrington conjecture or other conjectures or theorems? I'm not sure. That's a very interesting question.
Well, for delta, there are these parking functions with undesirable spaces. There are these Tor interpretations, conjectural, you know, due to Carlson Mellett for Loehr Warrington. So I guess
yeah.
So Anna, do you know, is there a delta version of the Loehr Warrington?
I don't know yet, but that is actually something that our group was interested, but I'm not sure if we have been working on it. There are like too many directions, but I don't know. Yeah.
I don't think I ever calculated that.
Now, is that mixed signs, the Schur expansion?
Yeah, well, there's a global sign in front of
Right.
nabla S lambda.
Right.
Okay.
That's easily
Oh,
defined.
right. So for Loehr Warrington, it's either sure positive or sure negative. But if I do
Right.
like delta EK S lambda.
Yeah, I've never tried that. So I was wondering.
I don't know.
Hi, Anna.
Hi.
Hi. I thought in your guys' paper, I thought you guys had paths under any line, including not rational endpoints. Is that not?
Yeah.
Wasn't that
That
the
was what
question
I was
earlier?
trying to say, like to Teddy. I'm not sure if that is related, because like in the definition for elliptical algebra, your M and N are integers. And so like we don't pick any just like random M and N. But Teddy was asking what if these are like any MN, right? But what I was saying is that like even though we pick the same M and N, we always shift it a little bit. So to make sure that it's not rational when we do the math, when like the M and N and the minus epsilon. So it's really under any line, as you said. But the definition still, I'm not sure, like when you define the elliptical algebra, would that be like another version that actually when you choose your universe, you don't have a rational, right? The M and N, instead of coming from rational numbers, what if there are any real numbers? I think that's what he was asking.
Oh. Cool.
Okay, any other questions or comments? Yes, no? All right, so we'll see you all on Thursday, I hope.
All right.
Thanks, Anna.
See you guys. Bye.